Okay, hi everyone. Sorry I messed up the mute of the stream for the first time, just when I wanted to try something new. So today we are with Giulia D'Angelo, and Giulia is a postdoc researcher at the Italian Institute of Technology in Genova, and she's with the event-driven perception and robotics group, guided by Dr. Chiara Bartolozzi. And today she will present us her work about attention, and not in the transformer way, as Giulia would like to precise. So we will look at the neuroscience-inspired attention and how biological system put attention on the stuff that comes in front of them. But I will let Giulia tell you more about it, since I'm completely ignorant in this field. So please, Giulia, go on. I will mute myself in the meantime and try to make up for the mess. Thank you.
Yeah. So thank you so much. Thanks also for having me. Yes, as Fabrizio was saying, I'm Giulia D'Angelo, and today I want to talk to you about what's catching your eye. So this is like the question that I asked myself during my PhD, and I'd like to ask yourself this question. So if you don't hear me clearly, please interrupt me. I don't know if you can unmute yourself and then interrupt me. If you have questions, please ask and interrupt me as much as you want. Okay, I think we can go ahead and start. So what's catching your eye? So as Fabrizio was saying, I am a postdoctoral researcher in IIT, the Italian Institute of Technology, and I worked in bio-inspired and neuromorphic systems to model visual attention mechanisms. So let's start from the problem that I had starting my PhD, together with lots of other problems, but this was the problem with which I started. So we have robots, and nowadays we think that robots can live with us, right? So we think that they can solve the daily tasks that we do not want to solve anymore, right? So to do this, we need the robot to work in low power consumption in an unconstrained environment, right? Because we want the robot to live with us in a dynamic environment. And we also want it with low latency. We want it all, right? So this was the question. I have a robot and I want all of this. Okay, then I asked myself, there might be someone that has already done it for me, someone that has already solved these problems throughout evolution, for example, nature. So as you can see, we have, like, for example, the koala that is doing visual search, the zebras that are running to escaping from predators, and the nice monkey that is interacting with the surrounding. These are all incredible tasks that nature has solved throughout evolution, right? So I take inspiration from nature. This is my why. Then the question is still, how do we define attention? Because if we have a robot that needs to be attentive to the world, this means that needs to react somehow to the stimuli, right? So this is the question that I asked myself. And please let me know if you don't hear the video, because otherwise it doesn't make sense, okay? Just let's see the video together.
Take a look at this. Okay, now, did you happen to notice anything odd? Watch again. See any changes? Don't worry if you didn't see that it's two different men. It means your brain is doing exactly what it should be. It's focusing on the meaning of the scene rather than on the irrelevant details.
Okay, can someone tell me if you heard the video? Otherwise, I will explain it. Let me see. All good, right? You could hear it. Amazing. Okay, so did you notice that was a different person? Probably no, because as in the video is saying, and as the guy is saying, what we do is that we basically are focusing on the meaning of what's going on. And this is what basically came out from these studies. These studies are done from Yarbus, and they're coming from 1967. And Yarbus is one of the main, let's say, pioneer in attention. So he was interested in trying to understand what attracts our attention when we look at a scene, right? So I don't know if you can see my mouse, but for example, in the first case where we see basically that we have like some person in the room, and then we have this trajectories like this. So this recordings are eyes recording, our eyes movement recordings, and these are done with this monster that was one of the first eye tracking. So as you can see here, the movements of the eyes are basically going from one head to another head, right? So basically we are nosing the situation. We are trying to understand, okay, are they chatting, talking, fighting? What are they doing? Here, instead, we are triangulating. So we are trying to understand if we recognize the face in front of us. And here we are saying, okay, foliage, 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 bear, I need to run. Okay. So the problem is that how do we define attention? How do we understand what is really interesting for us or salient for us? It's very difficult. And this is what came out from Yarbus. It came out that we need to understand, and we understand the scene. We try to understand the scene as much as we can. Then we have an image, we have a scan path, and the scan path is exactly what I was saying before, right? The eyes movement recording, so the eye recordings. And then we have the saliency map. Why I said salient? Because it's very different from saying interesting, okay? Salient is something that caught our attention visually. And we see it here because it's basically a concretization of the scan path. So where we fixated the most in the visual field, right? Then in 1998, E.T. Koch and Niebuhr tried to create the first saliency-based model. So they were doing feature extraction, color, intensity, and orientation. Then they were doing, of course, the pyramid to make it scale invariant. They were doing some certain surround extraction. And then with a winner-take-all, they were trying to understand what was the most salient area of the scene, producing a saliency map as the one that you see on the right. Then, okay, amazing, cool. But feature extraction is not enough, right? Because how do we then perceive items around us? How do we use these features that we extracted from the visual field to understand that we have things around us? Okay, then the response comes from Gestalt principles. The Gestalt principles are basically the principles that we use to perceptually group the scene, to understand the scene. And one of it is, for example, closure. So usually humans, what they do is they try to understand as much as they can if they can recognize what they have in front of them, right? So the closure tells you that you will fill the gaps in order to understand that there is a dog that is walking, there is a triangle, and there is a square, right? Because this is something that you might recognize as familiar. Then there is the similarity. The similarity is another principle that tells you that you are much more likely to group things that are similar together. The same for proximity. You are much more likely to group things that are next to each other. And the same for figure ground segmentation. The Gestalt principle tells you that it's very important, and I mean, it's obvious, to understand what's figure and what's foreground and what's background. All of these guys comes from 1950. And then in 2000, we have someone that actually found these cells in V2. These cells, as you can see, so if you just imagine in A, B, C, and D, if you imagine this black circle here as the center of the receptive field, you can see that regardless of the color, and I can tell you regardless of the sides, because I've read the paper, you can see that this cell is responding on the edge only if the object is on the left. Okay, so you see a nice response here because the object is on the left, and a spurious response here, that is basically a spontaneous response here because the object is on the right. So let's take a closer look on this. Then if we just try to understand, like just imagine that we have the same problem of the closure here, right? And we just think about a possible shape of this cell, right? And we think that is like half moon, or as I call it, banana, okay, a banana shape. And then we think that we have different orientation of the banana shape. Then if we then group the information and the response from all of these banana shapes of different orientations, we might recognize that there is an object inside. These cells are called border ownership cells. Why? Because they tell you the ownership of that edge. Okay, so if that edge belongs to an object or not. So basically, this is all of the concept behind the border ownership cells and the border ownership filter. That is the von Mises filter. That is the filter that has been used here in 2014 from Russell et al. They extended the model that I was showing to you before. And what they have done is basically these two layers. One layer of border ownership pyramid, where you actually try to detect an object where, I mean, actually, this object is not called object, it's called proto-object. It's an object to be, because following the closure principle, you might recognize that there is an object, but you are still not certain, okay? Then you must be attentive to that salient area, okay? And then you have the grouping pyramid here, okay? So that is basically, I convolve with my filters with different orientations, and then I pull the information, right? I just sum up the information. So in this case, they had the intensity, color opponency, and orientation channel. Then if we, first of all, let's see the nice citation, but anyway, if we just go back in time and we think about the problem that I was having at the very start, right? I had the problem of the robot, and my robot is ICAB. ICAB is the humanoid robot at the Italian Institute of Technology. And ICAB has event-driven cameras mounted on it in our neuromorphic version of the ICAB. Then what I thought that was interesting for me, it was to have a channel of intensity. So a channel that was taking directly from the cameras, the events, right? The raw events. Then I needed, in my opinion, a depth channel, right? Because the robot needs to understand the depth of the objects, because it needs to understand if it can interact with them or not. And then the last one, motion. Why motion? Because motion is inherently an attentive signal, is indeed part of alertness in the attention scheme. Okay, I don't know if you are familiar with the bi-inspired camera, the event-driven cameras. I'm gonna go very, very fast, and you tell me if you don't know about it. Anyway, this is basically what's happening when we have frame-based camera. So what we have is that every chunk of time we try to get a frame. Then if we have, for example, a bottle in front of us and the bottle is always static in the same space, in the same place, and it's not moving, we get the frame with the same information, right? But then the bottle is moving in between two frames. So it's moving that fast, that is moving in between two frames, we completely disregard the information, which is like undesirable, right? So if we just think that we are, just throwing, I'm just throwing at you the bottle, right? And we use event-driven cameras in this case. And instead of, sampling in time, we sample depending on the y-axis, so depending on the intensity. And we get an event every time that there is an increase or decrease in light. This is what's happening. It's happening that I will have a nice, in high temporal resolution, a nice response in events from the event-driven cameras. And these are the events that carry on the information of X, Y, timestamp, and polarity. So these are the event-driven cameras. And this is one of my colleagues just moving the hand in front of the camera, and they have microseconds latency, and of course they're very nice for their power consumption that is very low. Okay, so let's go back to the problem. We have the event-driven cameras, the nice high cap, 200K euros of humanoid robots, and then we have this 3-channel intensity, depth, and motion. Then if we have a little bit patient on it, you get the bi-inspired saliency-based attention model, which is the model of my PhD, what I have done during my PhD. So let's see if in the chat you have okay, if you have some questions. No, it seems everything clear. Okay, let's go ahead. So basically, this is what I've done during my PhD, and you can see that we have intensity, depth, and motion channel, as I was saying before. Then let's start with the intensity one. So we basically reproduced and adapted a model that was already present for the RGB cameras, and we adapted it for the event-driven cameras. So we have positive events, negative events, and we go directly to the border ownership pyramid. Why? Because they do center surround extraction that we do not have to do, because the center surround is giving you the edges of the scene. And we can assume that event-driven cameras gives you directly the edge map of the scene. So we basically got rid of 2 layers of processing, and this is of course cool in terms of computation. So this is the very first model that we have worked on, and then you can see the events. You can see the saliency map. So ICAB is looking at the objects and is producing a saliency map online. I will tell you the latency later on. So we see that as a nice response. And then if I just go with something else, it's attentive to my paddle. This is just to say that we go up to 2000 pixels per milliseconds to the generation of the saliency map. Okay, then I moved to the depth, because I wanted also the depth information. And then with Shuman Ghosh, that now is a PhD student at Guillermo Gallego's lab, it was my master thesis student at that point, and we've done together the disparity structure, this cooperative stereometric model based on the publication that Mosen and Conrad has done, that is basically based on the solving the correspondence layer, in a nice and easy way for event-driven. So you see that we have the left camera events in this case, and the right camera events in this case, and then we get the disparity map, and every disparity map is actually our new input to the border ownership pyramid. So if you just think about it for a second, what is has the higher disparity has the less and the lower depth. So basically what's happening is that I want to be the robot to be attentive to what is the closest object, right, to him, to it. Makes much more sense. Okay, so what I want to show to you about this very project is this thing here. Okay, so you can see here, whilst it's building up, that we have the RGB video, the rectified series events, the disparity map, and here we have the attention of the intensity, the model, the first model of the intensity that I showed you before, and then here we have the response of the model with the depth information. Okay, just focus on this too. So what's happening is basically that right now we only have a bottle, but what's happening if I put another object? If I put another object, the attention here, if you don't have a clear task, is jumping from one object to another object, right? Instead here is focused on the closest one, as I was saying before, right? So we solved the problem, because of course it's undesirable that the robot would be attentive to more of one object if he needs to interact with it. Okay, so we of course compared it with the RGB model, and you can see that we are a little bit much more let's say precise, I mean localized on the object, because
not everyone is familiar with event cameras, but I was noticing that the iCube vision field ICAB, vision field was moving with some movements just to make the bottle appears actually, because if the eyes were still, we wouldn't be able to see the bottle, right?
Yes, of course. So what we do is basically doing nice circular movements that are resembling the movements that we do to see, because it's the same for us. If we think that we can look at the scene without moving our eyes, but it's not true. Actually, this is what we do. We do microsaccades to see what's going on in the visual field. So this is what we do with the neuromorphic ICAB too. Like we make the ICAB to perform these small little movements, because as you said, otherwise we wouldn't see anything.
Okay, thanks. Please go on from the proximity attention. Sorry, from the proximity view.
Let's go ahead. Let's see if we can bring home this talk. So I compared, I saw on Discord someone that was asking for the code. Please do ask me for the code. I have code for C++, PyTorch, whatever you want. Brian, I have like lots of different implementation of the same thing. So please just ask me, okay? I will give you my email at the end. So just ask me and I will give you everything you want. So here is just a comparison of the input, the depth math, and then we are comparing the event-driven saliency map with the RGB saliency map. And as you can see, we're a little bit more precise, mainly because our input is much more sparser. And is, of course, like we work with events. So it's a little bit better in this regard. So we have done a bunch of different comparisons, looking at different kind of metrics that are out there and as a state-of-the-art metrics to see if our results are close enough to the saliency map that are actually coming from humans. So we are trying to validate with fixation maps coming from real subjects that are looking at the same scene. And it seems that we perform better looking at this metric that is the structural similarity, mainly because it's looking at the structure of the scene too, I think, or I kind of understood throughout the years. But still, we have the problem of the bottleneck that we have is still there, the fact that we need to deal with all of these events. Then a way to deal with these events is working with spikes, then trying to work with something that works amazingly with events, right? So this is Spinnaker. Is a board with which I worked on, and I have done mainly these two channels because I wasn't satisfied of the intensity channel as it was running on GPU, and I wanted the intensity channel actually working in the fully neuromorphic way, so using Spinnaker. And then I used Spinnaker also for the motion channel. So let's go to the intensity done on Spinnaker. Basically, this is what we have done. I've done a spiking convolutional neural network, and I've created, layers of the von Mises filters with different orientations and different scales. And then thanks to the connections, I was able to detect proto-objects in the scene. This is just a response of the saliency map coming from the model of very stupid cases. But it's just to understand and characterize the model a little bit. So you can see that we respond to the circles, we respond to these objects that are in the scene, and we respond only to the object and not to the clutter because of the way the events are working, because we have too many positive and negative events, and then we don't create the nice proto-object detection with these filters, which is cool because we don't want to be attentive to clutter. Then we have done the same comparison to the NAST 3D RGB images. This is a data set. The NAST 3D is a data set. And then as you can see, these are the saliency map coming from the SNN that I've done. Chaos, a little bit less chaos. And here, And here is the fixation maps coming from subjects, real subjects. As you can see, still chaos, but a little bit less chaos. I have done, again, here are all of the metrics I was talking about before. So we have the structural similarity, NSS, and other metrics that we use to compare with the saliency maps. They're like just specific for saliency map. And maybe the important thing is that they're not that significant, because as you can see, even though changing the overlap of the neurons, so placing the neurons far apart or overlapping the neurons didn't change that much. You can see that the results are basically the same, and they're not that good. The best one seems to be the AUK, JUDD. Then this is basically the slide that makes sense the most, because like we have, for example, here we have two examples of proto-object and non-proto-object. Yes, tell me.
Yes, I was wondering, maybe you didn't mention it, but actually the spiking neural network that you are running are with handmade filters, right? Not with trained one.
No, yeah, they're I would say are coded rather than handmade. But
yeah, handmade, I mean, you didn't train them via backprop, let's say.
Yes. No. They're not trained. This was actually something that I wanted to do. But you know, I just had 3 years and a half to do the PhD, but it's something that I wanted to do, is to train it to see if the filter that was coming out was actually the same filter that I was using, just to prove myself that I was very cool and nice and I used the right filter. But no, these are coded, yeah. Again, trying to resemble, you know, it's like kind of when you use the Gabor filters, they're kind of resembling what's going on in the V1. This is the shape that we thought makes sense for those cells, but we still don't know the shape of those cells in reality, so in the cortex, and we still don't know if you train it, then it comes out what we used. But it works. So it would be a nice thing to do. Actually, if you want to do it, we can talk about it, like, honestly. So if you don't have any other question, I can go ahead. Let me know. Yeah, okay, I will take it as a no. So here we have the proto-object and the non-proto-object example. So we have the stimulus. This is called proto-object because if you remember at the very start, like basically 3 days ago, when I was starting this presentation, you can see that I was saying, you know, the closure Gestalt principle, right? So these resemble the closure Gestalt principle, and these for us resemble the proto-object, okay? So you can see that here for the event-driven proto-object, so the intensity channel, we have a nice response inside the proto-object, and then we have some error here, basically some spurious response. And the good thing that is that, like, I have the code that is running on C++ for CPU and on GPU in PyTorch, and I mean, is kind of taking 100 milliseconds to generate the saliency map. Instead, if you use the DAPT channel, so the channel that I was doing with the master thesis student, this takes 170 milliseconds. Why? Because you have 100 milliseconds plus the milliseconds that you need to compute the disparity. And then the intensity channel that has been done with Spinnaker, it goes down to 16 milliseconds, which is actually very cool. But this is in simulation. And in simulation, the 60% of overlap is requiring 48,000 neurons. This means 6 Spinnaker boards. This means unfeasible, because if you just plug 6 Spinnaker boards on iCub, you're never gonna move it, and it's really not feasible. So something is coming soon, and I hope I will have good results to show you guys. And this is the spec, and is actually the device that is used and done by Sense. I think you might know it, and I'd like to understand if attention here makes sense. It should make sense because, again, it's a spiking convolutional neural network device, and it should, like, having the DVS attached directly to the chip, like, should resolve my life. And let's see what I will get out from it. So let's go ahead and let's stay with Spinnaker. The last channel is the motion channel, and the motion channel, if you can see here, it doesn't go from all of the proto-object thingy. Why? Because if I throw a ball at you, it's inherently interesting. You don't care what going in towards you, right? You don't care if it's a ball, if it's a bottle, you don't care if it's an object or not. You just care that you need to run if something is coming towards you. So here you do not. Yeah, Fabrizio.
This time it's not me, it's from the chat. They're asking if you can share the Spinnaker code for
the attention.
Yes.
Sure. Yeah, I will give you my email, and you are obliged to send me lots of emails asking for the code. I will give it to you for sure. Thanks to you. So basically, this is the motion channel, and the motion channel basically is based on the spiking elementary motion detector. That is this one here. So spiking elementary motion detector, where you have neurons that are able to detect left to right motion, right to left motion, top to bottom, bottom to top. So the cardinal directions. What I thought at the very start of my PhD, I was very naive, and I just thought, oh, why don't we use the same architecture that we have in the retina? So the eccentricity. And then why we don't downsample the visual field as we downsample it in our retina, which is eccentric. And eccentric is not because I am eccentric, but because it has receptive fields in the fovea that are smaller and receptive field in the periphery that are very big, and they acquire a coarse information of the periphery of the visual field. Indeed, when you need to focus to an object, you will foveate to the object. Why? Because you need to put the object in the center of your retina, because you have the area that is much more densely resoluted with cones and rods, cones mainly. So said this, this is what I've done. I have done this eccentric downsampling, then I attached it to the spiking elementary motion detector, and all of this was running again on Spinnaker. And then here we have some nice results. I worked with synthetic and real world data. And then here we have just different stimuli, so left to right, right to left, and etc. And you can see that the model is responding nicely to the preferred direction. The preferred direction means a neuron left to right that is responding to left to right, and is not basically not responding to the anti-preferred direction, which is the opposite one, which is the right to left for the left to right. Then we can see here that we have the uniform downsampling, so the very first implementation of the spiking elementary motion detector, and the eccentric downsampling. And we can see that the mean firing rate required, and it's the gray one, the mean firing rate required for a different speed to detect the motion direction is significantly lower. And this is because not all of the visual field is triggered depending on the speed, because some of the receptive fields, especially the receptive fields that are bigger in the periphery, are selective, much more selective to higher speeds. So this means that even though I have basically doubled the number of neurons, because I have my neurons are overlapped and etc. and so on and so forth, I require less mean firing rate because my structure is a little bit smarter than a classic uniform downsampling. And here, this is the question of reviewer 2 is always fucking reviewer 2. And he was like, oh, but then if you have left to right and right to left and the 4 cardinal direction, it means that you can detect the transversal motion. Yeah, of course, yes, but I needed to prove it. And he wanted this graph, and I'm going to to show it to you because at the end is night. So you can see that I can detect that this is left to right and top to bottom. So I know that it's transversal from the left to right. So we got it to the end, guys. It has been very difficult. So the very question that I had at the start is that I want this robot to be attentive on the scene with low power consumption, unconstrained environment, in an unconstrained environment, and with low latency. And then I want to detect objects or proto-objects in intensity I have to be attentive to something that is moving, maybe because I want to catch it, right? And I want to be attentive to something that is next to me because I want to interact with it, right? So I can say, and I can conclude that I have done it and I solved the question that I had. I work with Chiara Bartolozzi at the Event-Driven Perception for Robotics Lab. He's in IIT, at the Italian Institute of Technology. And I tell you, thank you. And this is LinkedIn, Twitter, me just coming from whatever, just flying. And this is Brains and Machines that I hope you are listening to, guys. Is the podcast that I'm doing with Sunny Baines and Ralph Etienne. And this is my mail. Thank you.
Oh my God.
I know, it's amazing.
No, I was laughing more for the sticker with you flying. With the strings getting out of your head.
Look at that.
But by the way, there were people interested in the podcast, so maybe if you want, just say what is it about, what you are doing with Sunny, so on and so forth. Just
so you can find basically the website just looking at the QR code, and let me know if these QR codes are working or not. But anyway, so I am one of the editor of Neuropac. I work with Neuropac and I worked closely with Sunny. And one day we were crazy enough to think that we could start a podcast because we don't have a podcast in our neuromorphic community. And we thought that it could be nice because we still need to prove that this neuromorphic, let's say, is working. People do not believe us still because it's much of a vision for now. And to spread the voice as much as we can, this was the idea that Sunny and I had to spread the voice about neuromorphic. And I actually got some interest also from investors. So I think that the voice is spreading nicely. And the Brains and Machines is a podcast basically revolving around the neuromorphic community and the event-based community. So the event-driven cameras too. And we are interviewing mainly Sunny because I have other 3 jobs in the meantime, but we are interviewing and then I am discussing with Ralph at the end of the interview things and the work done from some of the figures that made, let's say, history in neuromorphic.
You will be happy to know that the QR code does not work.
Nice.
It says you need to choose a plan to reactivate this QR code. So
geez, every time. Okay. Yeah, because I'm just so poor. Whatever. Let me write in the chat.
You can drop it in the chat. Yeah. By the way, somehow I managed to make the YouTube streaming work. I don't know why. I don't know how. I just want some penis drawing on my laptop right now, and that's it. Because I love Zoomers. And there is also a technical question from Cameron. Have you tried the density-based clustering or spiking YOLO methods?
No, I haven't tried the spiking YOLO methods. The density-based clustering, can you tell me a little bit more about it? Like, can you be unmuted and we can discuss this?
Yes. Promise me you want the screen. Where is he? Cameron, are you still with us? Please, Cameron. Ask to unmute.
Let's see.
Let me get a meeting room real quick.
Nice, you were in pajama. Say the truth.
No, don't worry. We have plenty of time, thanks to me. And all the mess that we, so yeah, but for spiking YOLO would, but for object detection, in the terms of attention, to put the attention on some objects. That was the question, I think.
Yeah, but the point is that, yeah, of course, I can try different things. There's plenty of different methods. What I want to do is to be inspired in terms of architecture. So I use like the proper filter that actually resemble the V2 idea of what's going on in the cortex and so on and so forth. Because if I want to be really smart or smarter than this, I could do any stupid deep learning saliency-based model and it would work.
So
way
basically
better.
you will put the real attention with the transformer.
Yeah. Yeah.
I'm joking, of course, I'm joking.
No, it
But,
would work. It would work for sure better in terms of
yes.
accuracy for sure. Yeah, Cameron, what do you mean? Thank you, Daniel. Cameron, what do you mean when you say the density something that you said?
Base clustering.
Yeah, density-based clustering. Hey,
Mm.
can you hear me?
Yes, I can hear you. Yeah.
Okay. Yeah, like for instance, like there's like the DB scan algorithm.
Mm.
It's like a spatial clustering algorithm.
Yeah, I heard something about it.
Yeah.
Mhm.
Well, like if you're turning events into frames, you can then use that.
Yeah, but then that is a clustering thing. And what I do is slightly different because I'm trying to understand proto-objects. This means, just to give you an example, this means that if I have a shuffle, is it a shuffle? Mansarda? If I have a shuffle and then I have a bottle, right, over it, or a desk, what I want is to get the bottle and not the desk. Okay, so that's why I try to use these filters with different orientations because they're actually detecting fuzzy shapes, which is actually something that you cannot do because the clustering is not that smart, right?
Yeah.
That's the reason.
Yeah. I was thinking more about like with combining spiking YOLO methods with clustering as well.
It could be, and then I'm gonna give you the response that I was giving to Fabrizio's before. There's plenty of different models, plenty of different models of how to do attention. How I chose to do it is in the bio-inspired way, let's say. So I'm trying to use filters that resemble what's going on in our cortex. So I'm trying to do this, but if you give me this idea, the response is yes, of course, I could try. If you want, we can try together, for sure.
Okay, yeah, fantastic talk.
Thank you.
Thank you.
Thank you.
Thank you. Yeah, I also believe that at the moment that the spiking object detection models have not been trained on event cameras data, as far as I know, because from object detection there is only the prophecy data set. So in that regard, they still play with recurrent vision transformer and GNNs and so on and so forth.
Could be.
So. And,
yeah, we don't have so many data sets at this point. I was like very close to do the first attention data set. I will. If I win, if I will win Marie Curie, I will.
Yes, let's put the grant money inside an event-based vision dataset. Okay, let me see if on YouTube there are any questions. I don't think there are.
So there is like here there's Madsduck. Is that correct? I think.
There you go.
For the filtering, have you convoluted some predefined filters? Could you please talk a bit about the filters and what do you extract using that? So thank you. So the filters that we use are basically the filters that the first RGB model was using, that are called Mises filters, and they're these banana-shaped filters. And what they extract is basically a kind of a corner. Okay, you can think kind of corner. And the point is that if you have a filter of this orientation and this orientation and this orientation, you should be able, with different scales and different orientation, to detect funny shapes, right? So this is the idea of using these filters. And what does it mean predefined? I think it's the same question that Fabrizio had before. They're not trained, and these are hard-coded filters. We just wanted them like this because we thought it was smart. Not me, like a bunch of like very smart people before me. I'm just using.
Yeah, like a Gabor
Like
filter.
Gabor.
Yes.
So the Gabor filters are much more used for V1 to extract edge orientation. So you have different Gabor filters of different orientation, but exactly as you said, it's the same principle. And when you have a Gabor filter, usually you have a bank of Gabor filters that they resemble an hypercolumn. I'm trying to do the same thing. I'm trying to resemble an hypercolumn of von Mises filters with different orientations.
Okay. Is it used in your Spinnaker code?
Is it where are you reading these things? Or it was just
Chat.
you?
They want they want
Is it using your Spinnaker curve? Yes. So basically what we were doing, it was like a spiking convolution neural network. So we were creating the same filter over and over on the visual field with different overlapping percentage. Yeah. Let me, you know what, you need to ask me on my, just write me an email, because I think it's private. The repo, the GitHub repo, I think is private. But I will give you things in Italian, in the Italian way. I will give it to you anyway, if you want it.
Maybe we
No
can either you provide us with the presentation, or you can drop the email in the Discord chat apart from here, because
yeah,
there it will be repeated.
Let me see. Let me just put the email. So I'm gonna put it here, and I'm gonna put it here too. What? Oh, wow. Okay. I think it's kind of that there are no questions anymore, right?
No, I don't think there are any more. So we can stop it here. Thank you, Giulia, again. Sorry for the Zoom booming. I will work my ass off to get a decent video between the two recordings.
It has been
And
a crazy
what is
experience.
happening? Penises
I was like,
Fabrizio, fuck you.
I was like, is it Fabrizio? It's like, why though?
At the beginning, I was thinking that you were drawing on the slide without noticing it, so I was fine. And then I started seeing penises, and I said, okay,
That's weird.
that's weird. But I don't judge, so but
Jeez.
maybe it was for the attention.
Yeah, exactly.
Okay, thank you
Thank
again,
you.
Giulia, and
Thank you.
talk to you soon. Bye. Thanks,
Thank
everyone.
you. Ciao, ciao. Ciao.